Hi everybody, welcome to our next set of fun video discussions. What we're going to do today is continue on talking about different ways to calculate entropy. So in the preceding videos and in class discussions, we talked about some sort of qualitative ways to understand changes in entropy. And then in a recent class, we saw our first example of calculating entropy change with respect to heat change. Specifically, we learned about how to calculate the entropy change for the surroundings by taking the opposite of the enthalpy change of the system and dividing it by the temperature. So that was our first concrete example of calculating some kind of useful change in entropy. What we're going to do in these slides, and this video is probably going to end up being the longest one we've had so far, what we're going to do in these slides is go through different ways to calculate the entropy change for the system. Now, as you're going to see on these slides, I'm going to start to drop subscripts like this here, S, that stood for surroundings. Anytime you don't see a subscript, what do you think that means? If there's no subscript, and this is chemistry, we're going to be referring to the system. All right, so all of these entropy changes that we're going to be talking about here are going to be all with respect to the system. So this this first slide shows the change in entropy for an ideal gas, namely the typical sorts of physical changes you can do to a sample of a gas. Now the gas isn't going to do any chemical reactivity. We're just going to squeeze it, expand it, heat it, that sort of thing. And so we've got here three equations, one of which I'll sort of derive for you in a minute, but let's just understand in a qualitative sense how these guys make some sense. So let's take the top one there. The change in entropy is equal to N, the moles of gas, C, the specific heat of the gas, times the natural log of the ratio of the two temperatures. Now, hopefully this makes some intuitive sense for you that if T2 is bigger than T1, all right, so we're increasing the temperature on our sample of gas, then the ratio T2 to T1 is going to be greater than 1, and the natural log of anything bigger than 1 is a positive number, which would then make the delta S be a positive result. So, bottom line, you heat a gas up, the entropy goes up. Simple enough. The second equation, V2 over V1. Again, let's expand the volume of our gas, so V2 is bigger than V1. V2 over V1 then is some number larger than 1, once again the natural log of which comes out to be positive. Of course, N and R, the moles of the gas, the universal gas constant, those of course are positive numbers, so the delta S would end up being positive for the case of V2 being bigger than V1. We kind of talked about that in class already with our box diagrams. If you expand the volume, the entropy is going to go up. It goes up because there are more arrangements in more space, and here's a way that we can see that quantified for the expansion of an ideal gas. Now, you know from the ideal gas equation, PV equals nRT, that pressure and volume are inversely related. So if expansion creates a positive change in the entropy, then the opposite effect will be seen here with pressure. So if P2 is greater than P1, so that would be equivalent to us compressing the gas, then P1 over P2 is going to be some number less than 1. The natural log of any number less than 1 would be negative, and that would cause, of course, then the entropy change to itself be negative. Because, again, squeezing a gas is analogous to reducing its volume, which would produce a negative change in the entropy. Now, I'm not going to go through the details of a derivation of all of these equations, but let's just take a look at the top one. And warning, there's going to be a little bit of the calculus, but I'm going to show it to you for those who kind of care about this sort of stuff. All right, so let's just start with some basic ideas. We know that the change in enthalpy for a gas would be equal to the amount of gas you have, N, times the specific heat of that gas, times the change in temperature. This is a good old mc delta T, except instead of mass, we're doing it with respect to moles. No big change there. We also learned in a previous class that delta S would be equal to the heat exchange divided by the temperature. So hopefully you're beginning to see what I'm going to do here. Now these deltas here refer to large changes, but in order to do some calculus, what we have to do is take small changes and add them all up. So instead of a delta H, I'm going to talk about a small change, a dQ, a small change in the heat, which would be equal to NC times a small change in the temperature. A small change in the entropy, ds, would be equal to a small change in the heat divided by the temperature. Now, if dq equals nc delta t and ds equals dq divided by t, then I can say that ds is going to be equal to nc dt divided by t. Now, here's where the calculus comes in. If I want to figure out the overall change, I need to sum up the small changes. So we will integrate ds with respect to s, and integrate nc dt over t with respect to t. So the left-hand side just becomes delta s. The right-hand side, I can take nc and pull them out of the integral because they're constants. So that'll become then nc times the integral of dt over t. And you calculus fans know that the integral of dx over x is the natural log of x. So the right-hand side becomes nc times the natural log of my upper limit, I'll call t2, divided by my lower limit, t1. So then I get delta s equals nc ln t2 over t1. And if you take a look back at the slide on the previous page, that's exactly what I showed you to begin with. Okay, so that then gives us three equations to find the delta S of an ideal gas. And we're not doing anything interesting to the gas. We're just heating it, cooling it, compressing it, expanding it. You know, those physical changes. Nothing chemical yet. All right, so let's go ahead and get changes. And here is our first example of calculating the entropy change now of a reaction. The form of this equation should look kind of familiar to you. These little summation signs and these little superscript zeros. These should look familiar to you. You have seen this equation before, except in the context of, do you remember? Enthalpy. You might remember doing enthalpy change calculations, delta H0, being equal to the sums of the heats of formation of the products minus the sums of the heats of formation of the reactants. Products minus reactants. Products minus reactants. You heard that quite a bit last year, and here it is, it's coming back. Now we can do this products minus reactants calculation because entropy change is a state function. Remember our curve? We only care about where we start and where we end up. That's a state function. We don't care about how we get there. We only care about where we are and where we're headed. So, you can do the entropy change calculation for a reaction by taking the sum of the entropies of the products and subtracting from that the sum of the entropy of the reactants. Products minus reactants. Now, let's talk about a few things. First, the little zero. Hopefully you remember what the little superscript 0 means. That refers to the materials, the components of the reaction, being in their standard state. And standard state is the state that the material would be in if you were at 1 atm pressure and 25 degrees Celsius. So the standard state for oxygen is obviously a gas. At 1 atm and 25 degrees, oxygen is a gas. The standard state for carbon would be a solid, because carbon at 1 atm and 25 degrees is a solid. So that's what we mean by standard state. Now, the individual entropies that we're going to be summing up here for the products and the reactants, as you can see, those are standard entropies. Now we'll talk a little bit about what standard entropy means when we get to talking about the third law of thermodynamics. But right now, what they're going to be to you and I is they're going to be numbers in the back of the book. To get those S0s, you're going to want to look in the appendix in the textbook, and you'll see tabulated there the heats of formation that you used last year, along with the standard entropies and the standard free energies of formation. Again, we'll talk about those later. So just to make sure we're all on the same page here, let's go ahead and do some products minus reactant calculations. Alright, so here's our first problem. We are going to do the oxidation, the reaction with oxygen, of nickel 2 sulfide to make sulfur dioxide and nickel 2 oxide. Okay? First thing you want to make sure whenever you do these reactions is that, of course, you are balanced. And I've already done that for us here. I can't do this calculation if my equations are not balanced. And then I've listed here, these numbers here are the standard entropies that you would look up in the back of the textbook, in the appendix. So I'm going to go ahead and do the simple products minus reactants calculation. So what I'm going to do, my delta S for the reaction is going to be 2 times the SO2 plus 2 times the nickel oxide minus 2 times the nickel 2 sulfide, 53, minus 3 times oxygen, 205. Alright, now, I actually haven't calculated this out yet, so I'm going to sit here and punch it into my calculator. Why don't you go ahead and do the same thing? Alright, minus 2 times 53 minus 3 times 205. Alright, so I get negative 149. Now, units. Notice the units of standard entropies are joules per Kelvin mole. I've multiplied through by the mole quantities of the balanced reaction, so that's joules per Kelvin. So that is the entropy change associated with this reaction. Energy per temperature. Alright, so there's the answer, and we want to explain the sign, namely this negative sign here. To explain the sign qualitatively, what you can do is look at the overall reaction. And you see in the overall reaction, I go from 2 moles of solid, 3 moles of gas, 2 moles of gas and 2 moles of solid. In order to predict the sign, what I'm going to look at is I'm only going to look at the change in the moles of gas particles. Solids have low entropy, so messing with solids isn't going to significantly alter the entropy of the system. But gases, which have high entropy, when I change those quantities, I'll see a higher change in the overall entropy. So, I started with 3 moles of gas, and I ended with 2 moles of gas. So my delta N here is going to be negative 1 mole of gas. So, if I lose gas moles, if I lose gas particles, I have fewer particles, fewer arrangements, so that should clearly indicate that the entropy change is going to be negative. Alright, so you can qualitatively predict what the sign of delta S would be based on the change in the moles of, again, let's emphasize this, gas moles. Alright, so we go from 3 to 2, loss of gas moles, negative change in the entropy. Fewer particles, fewer arrangements, less entropy. I want to emphasize again that what we're doing here is this is the change in the entropy of the reaction, i.e. the change for the system. I've only determined the change for the system. Now, what does that tell me? Is this reaction spontaneous or not? Think for a moment. I know that the entropy change for the system is negative. Does that tell me, according to the second law of thermodynamics, whether or not this is spontaneous? The correct answer is, I don't know yet. Remember, the second law of thermodynamics tells me I need to calculate the delta S for the universe. Here, I only have the delta S for the system. So, even though the system's entropy is negative, the possibility that this could be spontaneous is still out there, because I don't yet know, again, the change for the entropy change of the universe. So don't get caught by that trick question. You can't answer spontaneity until you know about the entropy change of the universe. More on that later. Practice, go ahead and do this additional problem. Why don't you go ahead, pause the video, and do the calculation for yourself, and then come back and we'll talk about the answer. And as you write out the answer, try to explain the sign. Okay? So go ahead, pause the video right now. Seriously, did you pause it? I bet you didn't pause it. You're still listening, aren't you? Okay, fine. Let's go ahead and do the problem. So let's type out the calculation. 2 times 28 plus 3 times 189 minus 1 times 51 minus 3 times 131. And so I get a delta S of positive 179 joules per Kelvin. Okay, seriously, pause the video now and try to explain the sign. Go ahead, pause it. Yeah, you didn't pause it again, I can tell. All right, so the sign is a positive change in the entropy. So let's go ahead and do the analysis we had before. We don't really care about the solids because they can't influence entropy. So let's look at the gases. All right, so we got 3 moles of gas there, and then we got, whoa, hold on here a second. I got 3 moles of gas there too. So based on that qualitative predictor I was talking about before, my delta S should be a lot closer to 0, because I went from 3 moles of gas to 3 moles of gas. But clearly the calculation is not 0, positive 179 joules per Kelvin. So here's how we're going to explain this. Hydrogen. If you drew the Lewis dot structure for hydrogen, you'd draw something like that. Hydrogen is not a very interesting molecule. There are not very many ways for hydrogen to wiggle and jiggle. It can bounce through space, and its HH bond can contract and expand a little bit. But other than that, there's not much for H2 to do. Meanwhile, water, if you draw the Lewis dot structure for that, you'll recall that it's bent. Water can wiggle and jiggle in a number of different ways compared to hydrogen. The bonds can expand and contract. The bond angle here can widen and narrow. And we can also get some out-of-plane wiggle and jiggle between the HOH planar molecule. So there are more ways for water to move around. The fancy term for more ways to move is called degrees of freedom. Sounds like a political term, I guess. And water has more degrees of freedom. It has more ways to wiggle and jiggle. In terms of energy, it has more ways to sort its energy. So if we have more ways to distribute a molecule's energy, then it's going to have greater entropy. And we see that in the standard entropies, 189 for water and 131 for hydrogen. So the increase in the entropy in going left to right here isn't about the number of gas molecules, but it's about the complexity of the gas molecules themselves. We've gone from a simpler hydrogen, simpler in terms of fewer degrees of freedom, to a more complex water with its additional, significantly additional degrees of freedom. More wiggles and jiggles, more ways to spend the energy, more entropy. Okay, we'll stop with that. We've just gone through different ways to calculate the delta S of a system. The 3 equations for an ideal gas, and products minus reactants. But notice we're still only talking about the delta S of the system here. We haven't included the surroundings bit yet, so I still really can't say anything about spontaneity because I don't know the delta S of the universe. We'll get to that real soon.